Hello and welcome to this lecture. Over the next few lectures, we shall begin our review of the basic principles underlying the governing equations of continuum mechanics, more specifically of fluid mechanics and the transport of heat or a single scalar at concentration. The idea over these next few lectures will not be to attempt a fully rigorous derivation of the governing equations. Rather, we shall try and better understand the equations by sketching out the derivation and by reviewing some key ideas behind the mathematical formulation of these equations. Now, a natural place to start is with the kinematics of motion, that is, with a mathematical description of how a fluid moves. So that's where we begin today, the kinematics of motion. So kinematics just focuses on describing fluid motion without worrying about what causes the motion. That is, without concerning ourselves with forces and stresses that give rise to flow. That subject comes under dynamics, which we will take up in the coming lectures. All right, so let's begin. So first, I'd like you to imagine that there's a fluid flowing across the screen. And to describe its motion, let's first start by setting up a fixed coordinate frame that is fixed. Let's say it's the laboratory fixed frame, so it doesn't move. Right, so we choose, let's choose for simplicity a Cartesian coordinate system. But whatever we do will be translatable to any other coordinate system, cylindrical, spherical, so on. All right. Now, in this system, imagine a fixed point in space, yes, which is described by the position vector that gives its position. Let's say its coordinate is x, the position vector. So x really is x1, x3. All right. Now, at this point, if there's a fluid flowing across your screen, and let's assume the flow in general is time dependent, then if we just focus at one point, what we already know and what you have been introduced to in earlier classes is the concept of a velocity field, which means that at every point, including this one, at every given time, you can identify or assign a velocity vector. Let's say this is the velocity vector v, and this is its value at some time t1. And at some later time t2 could be something else, right? So this is the same v at a different time t2. Now the idea here is that, of course, as time progresses and for all points in the domain, you would have such a field varying as a function of space and time. So this is v written as a function of spatial coordinates and time. This is what we call the Eulerian velocity field. Okay, so this is something you're already familiar with. However, I would now like to raise a conceptual problem with this picture, which might have been bugging you at the back of your mind, but it's something that one doesn't typically think about too much in an introductory fluid mechanics course. But this is exactly the sort of subtlety that we want to pay some attention to in this sort of, let's say, intermediate level course. All right, so the question is, what exactly does this Eulerian velocity field mean? By that I mean, if we focus at a fixed point in space, how can we think about this fluctuating velocity vector? Well, the problem arises because we define velocity as the rate of change of position of a macroscopic body, of a mass point in Newtonian point mechanics, or in the case of a continuum, it's the rate of change of position of a point in the fluid. But right now we are focusing on a fixed position in space, and the fluid is moving past it. So it's not immediately clear what this velocity means. What point is moving with such a velocity? Certainly not the fixed point x bar at which we are defining this Eulerian velocity. So that's the confusion. And the reason this is confusing is really because a much more natural way to think about fluid motion is not in the Eulerian frame where we focus on fixed points in space, but rather in the so-called Lagrangian frame where we move with the fluid. A better term than Lagrangian frame is a material coordinate frame because we're focusing on a fixed material of fluid as it moves. So let's take that up for a bit. So what we're saying is, now imagine again in the same fluid that's moving across your screen, at some reference time t0, let's focus our attention on some material of fluid. Yes, now this material, this packet, let's say, of fluid, is a macroscopic packet, and it contains a whole bunch of points within it, enclosed within this boundary that I shall call, this boundary I will label as dVm, and this entire volume is Vm, where Vm denotes a material volume. It is nothing but a volume of fluid, or a mass of fluid, or a piece of fluid that moves with the flow. So yes, so this material volume has points within it, and the idea is at some time t0 we can use the spatial position of this point to label it essentially. So let's choose one representative point, and its label is going to be x0, where x0 is simply spatial position at time t equal to t0, our reference time. So now this x0 serves as a coordinate that labels the point of interest. All right, so if we focus our attention on this piece of fluid as the fluid moves and wait for some later time t1, what would happen is this point would move to some other position here, which I will label x. So x is the spatial position of this point at some time t1. And not only this point, but all points contained within the material volume would move, meaning that the volume itself would move and occupy a different shape. And in general, the volume itself could change if the fluid is compressible. So this is where we are now. And the idea is we are now focusing on tracking this material point, or the material volume that contains all these material points. So now what we have is we really have a transformation, a time-dependent transformation that gives us the current spatial position of a point labeled by x0 as a function of. So what this means is, if I change my focus to different material points, I basically change x0, and every such x0 will have a different spatial position depending on the time t. So this is a mathematical function, or a transformation, that transforms x0 to x. In other words, tells us what the current spatial location of fixed material point is as it moves in the flow. So now with this picture, yes, I should make another introduction here. So this x0 is what we will call the material coordinate. Let me write it here. These are the material coordinates, or as they're also called in the literature, the Lagrangian coordinates. So that is what x0 is, whereas x is the spatial coordinate system, or the Eulerian coordinate system that we saw earlier. All right, so now that we have this mapping which tells us how the spatial coordinate of a material point changes, we can now immediately define the velocity of a material point in a very natural way. So we are interested in the velocity of a material point. This is nothing but the velocity of this point as it moves in the fluid, which now we can apply our normal idea of a velocity as the rate of change of position. So this velocity, which now is a function of the material point we choose and time, is nothing but the derivative of the spatial coordinate mapping. where this derivative is being taken while keeping x naught constant. So you see, by thinking about material points and by tracking material points as they move with the fluid, we can find a natural definition for the velocity as the rate of change of the position of the point as we move along with it. So this is what we would call the Lagrangian derivative. That is a derivative that we take as we move along with the fluid, or a derivative that we take while fixing our attention on a fixed material point. So in words, I would say that the Lagrangian velocity is nothing but the Lagrangian or material point velocity is defined as the Lagrangian or material derivative of the spatial position. Right, so I hope this idea is clear. So now we have a clear definition of the velocity, but the velocity for a fixed material point, or a velocity as the point moves in the fluid. Now from this we would like to backtrack and ultimately obtain a meaning for the Eulerian velocity field. So how does one do that? Well, that is based on the idea that once we have the forward mapping of a point x naught, that is, once we know how x naught is transformed to x, we can always go backwards in time or invert this mapping and find out if how x naught is related to x. That is, I can go back and forth between the inverse mapping. So what this means is that if you tell me to look at a certain point in space x at a given time, I can always find out what material point is passing through that fixed location in space. Yes, because let's say at some point in space, let's go back here. At this fixed point in space, as time changes, I have different material points moving past it. At any given time, I can find out what material point is at this location by backtracking the video and seeing where it came from. In other words, if I play the video back from time t1 to time t0, I would find out where this point came from, and I would thereby be able to find out its material coordinate. And if I know its material coordinate, I can then use the material velocity definition to figure out what the velocity is at that fixed Eulerian location at the time of interest. So to say it again, if I want to know v at t1, or what is the meaning of the Eulerian velocity field at time t1, well, it is the material velocity of the material point x naught that happens to be at the spatial position x at the given time t1. And this is made possible because this mapping, the mapping that represents the flow, is invertible. So it means that I can play the movie backwards and the mapping still exists. This is what is called a one-to-one mapping. And it's a basic idea integral to what we mean by the continuous flow of the flow of a continuum. All right, so what to say, to rewrite what I said in words, in words in mathematics, the Eulerian velocity field, right, which we know to be v of the spatial position, function of spatial position in time, can be obtained from the material velocity field by using the inverse mapping. Yes, so if I want to distinguish the two, let me put a subscript here and say this is the material velocity, this is the Eulerian velocity. The Eulerian velocity is the material velocity if I use the transformation between material coordinates and spatial coordinates. All right. Okay, so this is a clear way in which we can understand what the meaning of the Eulerian velocity field is, and it gives us confidence in defining such a field. But now in practice, this is not really how we define or calculate the Eulerian velocity field. Rather, we have partial differential equations that we solve that directly give us the Eulerian velocity field. Of course, there are some particle tracking experiments where you release tracers into a fluid and track the velocity of these tracers. In those experiments, what you're really calculating is this material velocity. And then from the material velocity, provided you have enough number of tracers, you can use essentially this formula that we have derived here to calculate the Eulerian velocity. But apart from such applications, we typically directly work with the Eulerian field. And really, this is the program that we will follow to derive the governing equations. The idea is that basic principles, whether it is the definition of a velocity or definition of acceleration, or the application of principles such as mass conservation, where we say that the mass of a given amount of fluid does not change. All of these principles, including that of classical force mechanics, all of these principles can be easily applied conceptually to a material volume, that is, to a volume of fluid as it moves along with the flow. On the other hand, it's much easier computationally to work with Eulerian velocity fields, Eulerian density fields. And this is why what we will be doing is applying our principles to material volumes, but then using relationships to transform quantities in the material coordinate system to the spatial or Eulerian coordinate system in order to get equations that are entirely defined in terms of the fixed Eulerian frame. So as a part of that program, one of the first quantities we would like to translate in this manner is the material derivative of a property, for example, temperature, concentration, or even a velocity component that is sampled by a material point. In other words, what we would like to find out is what is called the Lagrangian or substantial derivative. That's what we will take up next. So to imagine an example, consider the classic example. Consider the classic example of flow inside a converging section. Now, you can imagine that as you approach the narrowing section, if the flow rate, let's assume that the flow rate is maintained constant, as you approach, the velocity should increase so that the flow rate remains the same. Right? So even though the flow, the Eulerian field may be, so I say the Eulerian field, the function uni of space, it's a steady velocity field. Nevertheless, if I focus on a material point that's moving through this flow, the velocity of this material point is going to change and keep increasing with time. And so I might be interested in how, let's say, the velocity of this point increases. So what is the acceleration of this material point as it moves? And you can see that this would be a non-zero quantity, even though the Eulerian velocity field may be steady. In the same manner, if the temperature increases as I move towards the throat, the temperature experienced by this material point will also increase, even though at any given fixed position in space, all quantities may be steady. So to calculate such the rate of change of quantities as you move along with the material point, or the material derivative, that's our objective right now. We want to calculate the material, or what's also known as substantial, or yet another term, the Lagrangian. Lagrangian derivative. So for this, let's first think about the Lagrangian derivative of a general quantity. So let's call it B, which has some Eulerian description. And B is some scalar quantity. It could be the temperature, it could be the density, or it could be a component of the velocity field. So we will just use B as a placeholder here. Alright, so what we want to calculate is we want to calculate the material derivative of B. This capital D dt is nothing but a notation which actually represents the total time derivative of B keeping x naught, the material point, fixed. Yes? So usually, because we don't want to keep introducing this x naught in notation, we replace what this derivative means by the notation capital D by capital dt. Alright. So what does this mean? In order to operate such a derivative, time derivative keeping x naught fixed, I first need to use the mapping between x and x naught. So I know B as a function of Eulerian coordinates x and t. So I replace the Eulerian coordinate x in terms of its mapping x naught comma t, this manner. And so now I can simply apply the chain rule of calculus. So firstly, let me operate the time derivative on the local dependence of B on t. What I get is that term comes from applying the derivative, this explicit time dependence. But now I have a time dependence that is implicit between the transformation mapping between x naught and x. So I also have the derivative of B with respect to the Eulerian x first. So because it's a vector, I'll have to do it component by component. Yes. Then, so the derivative of B with respect to the coordinate x1 times the derivative of x1 with respect to t, keeping of course the x0 position constant, and I'll have to cycle over all the coordinates, all the components of the coordinate. And so on. Yes, but what are these? These are defined as nothing but the material velocities, right? The components of the material velocity. And these three partial derivatives of B with respect to spatial position will be recognized to form the gradient vector. So I can write this in vectorial form quite simply as the partial derivative of B with time. This is the so-called Eulerian derivative because it's a local derivative at a fixed position in space, times the velocity vector dot producted with the gradient of B. Yes, and this is equal to our substantial derivative, material derivative. So this is an important result because what it does is it gives us a way to calculate the material derivative, that is the derivative of a quantity B as you move along with the material point, entirely in terms of Eulerian quantities. That is in terms of the Eulerian derivative of with time at a fixed spatial position, and by knowing the Eulerian velocity field at point and the gradient of B at that point. And so at every point in space, every fixed point in space, we can calculate this quantity, this material derivative, which is nothing but the material derivative of a material point which is passing through that Eulerian fixed point of interest. So you see that this is in keeping with our program to represent material quantities in terms of the Eulerian. Alright, so now you will already start to see the usefulness of what we are doing, because this substantial derivative or material derivative of quantities appears all over the place in our governing equations. As you would recall from our the last lecture where we briefly reviewed those equations. However, we are not yet in a position to begin deriving the equations, because if we want to apply the principles, the governing principles, for example, mass conservation, we cannot really apply that principle to a single point, because in a continuum, we can't ascribe mass, let's say, to an infinitesimal point. Even less can we talk about stresses or pressure forces acting on a point, since these forces are forces acting on surfaces. Even the gravitational force, which is a body force, acts on a fixed mass, and it doesn't really act on a, we cannot think of it acting on an infinitesimal point which has no defined mass. Therefore, in order for us to apply the governing principles, we need to understand how the material derivative, how to define the material derivative, not of a single material point, but of an entire material volume. And this will be the focus of our of what we're about to do right now. But before that, there's another important point that I should point out with regard to the material velocity. So note here that what we did here is to follow single material point, and we have a well-defined definition for the material velocity. So from this itself, you can see that by no means can you think of a material point as a molecule of fluid. Why? Because a molecule of fluid is something that has a random fluctuating velocity. It might have a mean drift, but certainly the velocity is not going to be a smooth function of time. Indeed, there is no place for molecular velocities within the continuum framework. A material point, although it's an infinitesimal point, it makes sense only in a continuum framework, and it has no direct relation to a fluid molecule or any other molecular entity. Very often in discussions, even in books, you will find an interchange of the use of fluid molecules when describing the continuum equations, and this makes no sense at all. Rather, once we adopt the continuum frame, all the quantities such as material points, material volumes, these can only make sense within the continuum framework. And it's the only way we can relate it to molecular framework is in terms of macroscopic observables, like the flow rate that one could predict, which could then be matched to an ensemble of phase averaged flow rate from a molecular dynamics calculation. So this is just a word of caution that when we are in the continuum framework, we should really think of the fluid as a continuum made of an uncountable infinity of these material points, whose motion is described by smooth mathematical transformations.